Hey guys, so that was a song by New Radicals. They were a 90s band. They pretty much had that one hit. I knew of the song growing up. I was about 8 years old when it came out, but it was kind of a classic for a long time. So the reason why I brought that up was because the band was called New Radicals, and today we are talking about radicals. And so some of this may be new, but a lot of this may be review. And so um, this is a whole unit, maybe even of 2 units in Algebra 1, but we're shrinking it in to one section of geometry. And having a strong foundation of radicals is really important so that we can do well with Pythagorean theorem and later on in trigonometry. So our objective today is I can simplify radicals, including rationalizing the denominator. All right, so radical product property. So the square root of A times the square root of B is equal to the square root of A times B, just as long as A or B are not 0. So, for example, the square root of 9 times the square root of 16 is equal to the square root of 9 times 16, which is equal to the square root of 144, because 9 times 16 equals 144. And that equals 12. If we did it a different way, the square root of 9 equals 3, and the square root of 16 equals 4, and 3 times 4 equals 12. They equal the same thing. So we can do, if we see the square root of one number times the square root of another number, it equals the square root of the two numbers multiplied by each other. Next, let's quickly review the perfect squares. So they are 1 squared, 1, 2 squared, 4, 3 squared, 9, 4 squared, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, and 225. It's really good to memorize these numbers, these perfect squares, because they are very useful when we are simplifying radicals. Okay, so the process of simplifying radicals. It's kind of like a 5-step process. So, or really it's a 4-step process with checking at the end. So first step, check if the square root is a whole number. So if it's not a whole number, we can't simplify it. It's as simplified as we can get it. But if it's a whole number, okay, we can simplify it, potentially. So find the biggest perfect square, 4, 9, 16, 25, 36, 49, 64, so on and so forth, that divides that number in the root. 3, rewrite the number in the root as a product. 4, simplify by taking the square root of the perfect square and putting it on the outside of the root. Then 5, check your work. You can check your work by putting whatever number is on the outside, squaring that number, putting it back in on the inside, and then multiplying those numbers on the inside together. And if you get your original number, you did it correctly. So note that a square root cannot be simplified if there are no perfect squares that divides into it. So you can just leave it alone. So like with square root of 15, 15 is a prime number. So, oh no, it's not a prime number. Only 3 and 5 go into it. 1, 3, 5, and 15 go into it. Obviously, none of these are perfect squares, so square root of 15 is good. Square root of 21 is also good, because it's 1, 3, 7, and 21 that go into 21, and none of them are perfect squares. 17 is a prime number, so 1 and 17 go into it, so there are no perfect squares that go into the square root of 17, so that's also simplified already. So let's do some examples. Write the following as a radical in simplest form. Okay, so the square root of 72. Let's see here. So I'm going to use a pen. All right, so we have the square root of 72. And we know that 36 is the biggest perfect square that divides into 72. So how I would start it off is, so we have like 4, 9, 16, 25, 36, 49, and 64. So obviously, because like 81 is not going to go into 72 evenly. 64 wouldn't, 49 wouldn't. But so what I can do is look for a number divided by 2. So 72 divided by 2 happens to be 36. So I'm going to be checking all the numbers 36 and lower because it's divided by 2. Because like 2 times something could equal 72. So I know that 2 times 36 equals 72, and therefore, since the square root of 36 is 6, I can say that this is the square root of 36 times the square root of 2. I'm rewriting the square root as a product of roots. So therefore, I get that it's equal to 6 radical 2. So I found the perfect square is 36, and I made it 6 radical 2. So for 27, the square root of 27, 9 is the biggest radical, perfect square that goes into it. So it's radical 9 times 3, or the square root of 9 times the square root of 3, which equals 3 radical 3. So I might be going a little fast. So if you need to pause to kind of copy down the questions, please pause, because I'm going to make this video as short as possible, but there's a lot of content to cover. So with 5 radical 32, we're going to ignore the 5 until the end. So it's going to be 5, and then we're just going to look at the radical 32. And 16 is the biggest perfect square that goes into 32. So we have 5 times radical 16 times 2, which will be 5 times radical 16 times radical 2, which is 5 times 4 times radical 2, because radical 16 is 4, which is 20 radical 2. 20 radical 2. Yep. So now we're going to be adding and subtracting radicals. There, we were simplifying a single radical. Now we're going to be adding and subtracting radicals. So we can only combine like terms with the same number underneath the radical. So for this one, there's a 3. So we have a 3, a radical 2, and a radical 3. So we can combine the radicals 3's. So it'll be 2 minus 4 radical 3. So 2 minus 4 is negative 2. So we'll get negative 2 radical 3. Oh, yeah. So we'll get negative 2 radical 3 plus 2. We are basically treating the square roots as variables, then combining like terms only. And like terms, again, are terms with the same number under it. Okay, so at first it seems like we can't add these two together because they aren't like terms. We have a 2 underneath the radical and an 18. But we can simplify the 18 because 9 goes into 18, and 9 is a perfect square. So this is 9 times 2. And so we can change that to be 3 times radical 2. So we have 4 radical 2 plus 3 radical 2, which would equal 7 radical 2. So that's adding and subtracting. Be careful because you might be able to simplify it, and then we can combine like terms. Like terms are when the number underneath the radical are equal to each other. So multiplying, when we multiply radicals, basically all you're doing, so this is basically a long multiplication problem. It's 7 times radical 10 times 4 times radical 15. So we only really multiply together things that are outside of the radical and things that are inside the radical. So we'll multiply 7 times 4, and we'll multiply radical 10 times radical 15. So we'll get 28 times 150. So 28 times radical 150. And then we will simplify radical 15 and bring out whatever we can to the other side. So it seems like 25 goes into 150, and it goes into it 6 times. So we can say 28 times radical 25 times radical 6. And so radical 25 is equal to 5. And 28 times 5 is equal to 140. So we can simplify this expression, 7 radical 10 times 4 radical 15, to 140 times radical 6. So key thing here, when we're multiplying, we multiply the numbers that are outside of the radical, and we multiply the numbers that are inside of the radical, and then we simplify what's inside the radical. That's basically what I just said. All right, distribution and radicals. So we're basically just, multiplying a bunch of times over. We are foiling here. So we're going to do 5 root 6 times 3 root 6, and we're going to do 5 root 6 times negative 2 root 3, and 4 root 3 times 3 root 6, and 4 root 3 times negative 2 root 3. So this time I'm going to use the box method. I have 3 root 6 and negative 2 root 3, and I have 5 root 6 and 4 root 3. So this box is going to be 15 root 36, and so root 36 is 6, so 15 times 6 is 90. So this box is going to be 90. We then, for this box, we have 5 times negative 2 is negative 10, and 5 times negative 2 is negative 10, and then radical 6 times radical 3 is radical 18. Now radical 18, 9 goes into it, so this is radical 9 times radical 2, or 3 times radical 2. So negative 10 times 3 radical 2 would be negative 30 radical 2. For this box, we're going to be multiplying 4 radical 3 and 3 radical 6. So 4 times 3 is 12. Radical 3 times radical 6 is radical 18. So we get 12 radical 18. And then radical 18, again, is 3 radical 2. So 12 times 3 is 36. So we get 36 radical 2. And then lastly, we have 4 radical 3 times negative 2 radical 3. So that would be negative 8. And then radical 3 times radical 3 is 9. Radical 9. So we get negative 8 times radical 9. Radical 9 is 3. So negative 8 times 3 is negative 24. So we have 90 minus 30 radical 2 plus 36 radical 2 minus 24. We can combine like terms. So the like terms are going to be 90 and 24, as well as negative 30 radical 2 and 36 radical 2. So we'll get 66 plus 6 radical 2. Whew, I know. It's complicated. There's lots of things going on. But basically, this is FOIL. We're just doing multiplication a bunch of times over. And if you didn't realize, not only is this going to help you for geometry, but it's also going to help you for your algebra diagnostic test, because there's radicals on it as well. All right, so now let's simplify some radicals. So here we have 5 plus radical 7 over 10. So a lot of you might want to be saying, 5 over 10 is 1 over 2. But we have to have it so that both the number and the radical can be simplified. And so we can't simplify radical 7, so there's nothing that we can do. We can't simplify 5 plus radical 7 over 10 any further. Okay, so with 4 plus radical 12 over 2, radical 12 can be simplified. So 4 times 3 equals radical 12. So we can say 4 plus radical 4 times radical 3. So it's really important that we keep the distinctions of plus signs and multiplication signs. So this is going to turn into 2. Radical 4 is going to turn into 2. So we have 4 plus 2 radical 3. So like 2 times 3. So we have to make sure that we distribute this divided by 2 to both the 4 and this 2. We don't have to worry about the radical. So we'll get 2, okay, or you can distribute the 2 to the other side. But so the 2's cancel out, and we're left with 2 plus radical 3. For this third one, we can simplify 180. So that is equal to 36 times 5. And so 6, this will become 6. So it'll be 15 minus 6 radical 5 all over 9. We can take out a 3 in the top to make it 5 minus 2. And then 9 is like 3 times 3. The 3's cancel out. And we're left with 5 minus 2 radical 5 over 3. 5 minus 2 radical 5 over 3. All right, now, so this is radical quotient property. Okay, so we have 4 more sections, really only 3 more sections. So the radical quotient, so division property, is that the square root of a over b is equal to the square root of a over the square root of b, just as long as these are positive numbers. So for example, the square root of 64 over 16 is equal to the square root of 64 over the square root of 16. The square root of 64 is 8, the square root of 16 is 4, and 8 over 4 equals 2. So if we instead did 64 over 16, which equals 4, so the square root of 4, and the square root of 4 equals 2. So they're both equal to each other. So this is just proving that this property works, or it's an example of this, that this property works. All right, so write the following as a radical in simplest form. So we would write that this is the square root of 3 over the square root of 4. So we're taking the square root of the numerator and the denominator. And then what's the square root of 4? Well, it's 2. So radical 3 over 2. And then something that we'll be using quite a lot over the next month and a half to 2 months, is rationalizing the denominator. The denominator of a fraction cannot contain a radical. To rationalize the denominator, rewriting a fraction so that the bottom is a rational number, multiply by the same radical. So we're going to need to multiply these fractions by a special form of 1, which contains the radical that's in the denominator. So I'm going to say that again. We need to multiply these fractions by a special form of 1 that contains the radicals that are in the denominator of the fractions. So for this one, since the denominator is radical 2, we're going to need to multiply it by radical 2 over radical 2. Because we don't want to change the value, so this is still a special form of 1. Like anything over itself is equal to 1. So this is a special form of 1. And we're multiplying it by the original equation. So 5 times radical 2 is 5 radical 2. And radical 2 times radical 2 equals 2. Because radical 2 squared is equal to 2. And so we have 5 radical 2 over 2. For the second one, 6 over 5 radical 3, we're going to multiply it by radical 3 over radical 3. It's a special form of 1, and we're multiplying by this radical. So it's going to be 6 radical 3 times 5 times radical 3 times radical 3. And radical 3 times radical 3 equals 3, so it's going to be 5 times 3, which is 15. But we're not done yet. So we have 6 radical 3 over 15. We can simplify this 6 and this 15. 3 goes into both of these. So 3 goes into both of them, so it ends up being 2 radical 3 over 5. And it's funny, because 2 radical 3 over 5 doesn't really look anything like 6 over 5 radical 3. But these two numbers are equal to each other, and this is after rationalizing the denominator, making sure that there are no radicals in the denominator. So, in this lesson, we talked about simplifying rational expressions. So, by finding the highest number that goes in to that radical and then separating it out and taking that perfect square out. We then talked about adding and subtracting radicals. So, by finding combining like terms, and a like term is a radical that has the same number in the radical. We then talked about multiplying radicals, where you multiply the outsides and you multiply the insides, and then you simplify the insides. We talked about distributing radicals, so that's basically foiling, and so it's a bunch of multiplying of radicals. We've talked about fractions of radicals, where we can only simplify radicals if everything works out. And then we also talked about rationalizing fractions, and that means we cannot have a radical in the denominator. And so we would have to multiply by a special form of 1, which includes the radical that is in the denominator. So I know that was a whirlwind. Try your best on the online quiz, and we will work on this in class. All right. Good luck, and I'll see you soon. Bye-bye.